Today we're diving deep, literally, into a topic that sounds like it's straight out of a disaster movie. Can tiny, unnoticeable tremors deep within the Earth actually predict massive, city-shaking earthquakes? Let's get into it. So picture this. You're standing on the ground, everything feels totally still. But beneath your feet, miles down in the Earth's crust, there's a constant subtle dance happening. Tectonic plates are pushing, pulling, and grinding against each other. Most of the time, this movement is slow and steady. But sometimes, tiny patches of rock get stuck, build up a little bit of stress, and then slip. This releases a tiny burst of energy, a microquake. You wouldn't feel these. They're like a whisper in a rock concert, completely drowned out by the noise of everyday life. Seismographs, those super-sensitive instruments that detect ground shaking, are the only things that can hear them. For a long time, scientists saw these microquakes as just background noise, the normal creaks and groans of our planet. But what if they're more than that? What if they're clues? This is where things get really interesting. Imagine you're bending a plastic ruler. Before it snaps in a big dramatic way, you can feel it starting to strain. You might hear tiny crackling sounds. Some scientists believe microquakes could be the Earth's version of those little crackles, a warning sign that a much bigger break is on the way. The idea is that as stress builds up along a major fault line, like the San Andreas Fault in California, the rock around it starts to fail in small, localized spots. This could create a specific pattern of microquakes. Maybe they start happening more frequently. Maybe they start clustering in a particular area. Or maybe the way the seismic waves travel from these tiny quakes changes, indicating that the rock is becoming more stressed and fractured. This brings us to the concept of foreshocks. Sometimes a major earthquake is preceded by smaller quakes in the same area. The 1975 Haicheng earthquake in China is a famous example. Seismologists observed a swarm of small tremors, and based on that and other signs, they issued an evacuation warning. Hours later, a magnitude 7.3 earthquake struck. But because the city was largely evacuated, countless lives were saved. It was a huge win for earthquake prediction. But here's the multi-million-dollar question. Why can't we do that every time? The problem is, for every time a swarm of small quakes leads to a big one, there are many, many more times when a similar swarm just fizzles out. The stress releases itself in a series of small pops instead of one giant bang. It is like hearing a firecracker and not knowing if it's a lone prank or the prelude to a massive fireworks display. Telling the difference is the holy grail of seismology. To tackle this challenge, scientists are now using some seriously cool technology. They're deploying vast networks of incredibly sensitive seismographs, sometimes drilling deep into the Earth to place them closer to the action. This gives them a much clearer picture of the microquake activity happening along a fault. Then comes the power of artificial intelligence and machine learning. Imagine feeding a computer the data from millions of microquakes from all over the world, along with information about which ones were followed by major earthquakes and which ones weren't. The AI can then search for subtle, complex patterns that the human eye might miss. It is like teaching a computer to recognize the earthquake-prone whisper among all the other geological noise. One fascinating area of research is looking at slow slip events and tectonic tremor. These are even weirder than microquakes. A slow slip event is when a fault moves over days or weeks, but so slowly that it doesn't create a sharp jolt. It's often accompanied by a faint, continuous vibration called tectonic tremor. Scientists have found that these slow, quiet events can actually transfer stress to other parts of the fault, potentially loading them up for a big, sudden rupture. It's like slowly and silently tightening a rubber band until it's ready to snap. By monitoring both the tiny, sharp microquakes and these slow, rolling tremors, we get a much more complete picture of the stress building up in the crust. Let's think about what this means for the future. Imagine a world where your phone buzzes not with a social media notification, but with a warning. Increased seismic activity detected in your area. A significant earthquake is possible within the next 48 hours. Please review your safety plan. This isn't about predicting the exact minute an earthquake will hit. That might always be out of reach. It's about moving from long-term forecasts like There's a 70% chance of a major quake in this region in the next 30 years, to short-term, actionable probabilities. This could revolutionize public safety. It would give authorities time to shut down critical infrastructure like gas lines and bridges, alert hospitals to prepare for casualties, and give people a crucial window to secure their homes and check on their families. It wouldn't stop the earthquake, but it would drastically reduce its human cost. However, we have to be realistic. We are not there yet. The Earth is an incredibly complex system. Every fault zone is different. The type of rock, the amount of water present, the history of past earthquakes. It all plays a role. A pattern that signals a big quake in Japan might mean nothing in Turkey. This is why global collaboration among scientists is so vital. By sharing data and comparing notes from different fault zones around the world, they can start to figure out the universal rules, if any exist. So what's the verdict? Can microquakes predict major events? The answer is a hopeful, maybe, and we're getting closer. They are not a crystal ball, but they are one of the most promising clues we have. By listening carefully to the faintest whispers from deep within our planet and using the most powerful tools at our disposal, we are slowly learning to interpret the Earth's language. Each microquake we detect and analyze is another piece of a colossal puzzle, bringing us one step closer to unlocking the secrets of these powerful and terrifying natural events. It's a reminder that even the smallest, most insignificant seeming rumbles can carry a world-changing message. Thanks so much for hanging out and exploring this with me today. It's a huge and fascinating field, and we've only just scratched the surface. If you found this interesting, do me a favor and hit that like button, and definitely subscribe so you don't miss our next deep dive. Stay curious, stay safe, and I'll see you in the next video.